Hello again, my physics students. This is Mrs. Buchanan, and this is flip video number 13. We are continuing our study of Newton's third law of motion, action and reaction. Let's revisit our big idea. For every force, there is an equal and opposite force. We will be covering two learning objectives with this video. Number 4, explain why the accelerations caused by an action force and by the reaction force do not have to be equal. Then we're going to talk about explain why an action force is not canceled by the reaction force. Hello again, my physics students. This is Mrs. Buchanan, and this is flip video number 13. We are continuing our study of Newton's third law of motion, action and reaction. Let's revisit our big idea. For every force, there is an equal and opposite force. We will be covering learning objectives 4 and 5 with this video. Number 4, explain why the accelerations caused by an action force and by the reaction force do not have to be equal. And number 5, explain why an action force is not canceled by the reaction force. First thing I do want to talk about, though, I want to revisit forces. And there are actually 4 fundamental forces. You've investigated several contact interactions and actually one long-range interaction. Are they all different? Or are they the result of a single fundamental force? At this time, physicists recognize 4 fundamental forces. One is the gravitational interaction. All objects attract one another through the gravitational interaction, which is an attractive force due to the masses of the objects. Magnetic force and electric forces, such as those that cause static clinging, are part of the electromagnetic interaction. The electromagnetic interaction is a force that holds atoms and molecules together, so it is actually responsible for all of the contact forces. 2 more fundamental interactions occur within the nucleus of the atom. The strong nuclear interaction acts between the protons and neutrons that hold the nucleus together. The weak nuclear interaction makes itself known in some kinds of radioactive decay. Physicists have long searched for ways in which these interactions might be related. The unification of electric and magnetic interactions was a triumph of 19th century physics. In the 1970s, physicists showed that the electromagnetic and weak interactions were part of a single electro-weak interaction. The ultimate goal is to show that at some level, all 4 interactions are really one. So let's visit our learning objective number 4. Explain why the accelerations caused by an action force and by the reaction force do not have to be equal. We talked in the last video about the boulder and the earth. The boulder pulls up on earth with as much force as earth pulls down on the boulder. The forces are equal in strength and opposite in direction. We say the boulder falls to earth. But could we also say earth falls to the boulder? The answer is yes, but the distance earth falls is much less. Although the pair of forces between the boulder and the earth are the same, the masses are quite unequal. Recall that Newton's second law states that acceleration is not only proportional to the net force, but it is also inversely proportional to the mass. Because Earth has a huge mass, we don't sense its extremely small acceleration. Although Earth's acceleration is negligible, strictly speaking, it does move up toward the falling boulder. So when you step off of a curb, the street actually comes up a tiny bit to meet you. Force and mass. So we talk about the firing of a cannon. When the cannon is fired, there is an interaction between the cannon and the cannonball. The force the cannon exerts on the cannonball is exactly equal and opposite to the force the cannonball exerts on the cannon. So the cannon kicks. This is related to the bell ringer we did the other day. On first consideration, you might expect the cannon to kick more than it does, or you might wonder why the cannonball moves so fast compared to the cannon. According to Newton's second law, we must also consider the masses. Let F represent both the action and reaction forces, m the mass of the cannon, and small m the mass of the cannonball. Different size symbols indicate the differences in masses and the accelerations. The acceleration of the cannonball and cannon are: cannonball is large F over small m equals a. The cannon is small f over large M equals a. Do you see why the change in velocity of the cannonball is great compared with the change in velocity of the cannon? A given force exerted on a small mass produces a greater acceleration than the same force exerted on a large mass. If we extend the basic idea of a cannon recoiling from the cannonball it launches, we can understand rocket propulsion. Consider air escaping from an untied, blown-up balloon. If the balloon is released and allowed to move, it accelerates as the air comes out. A rocket accelerates in much the same way. It continually recoils from the exhaust gases ejected from its engine. Each molecule of exhaust gas acts like a tiny molecular cannonball shot downward from the rocket. A common misconception is that a rocket is propelled by the impact of the exhaust gases against the atmosphere. In fact, before the advent of rockets, it was commonly thought that sending a rocket to the moon was impossible because of the absence of an atmosphere for the rocket to push against. This is like saying a cannon won't recoil unless the cannonball has air to push it against. This is not true. Both the rocket and the recoiling cannon accelerate because of the reaction forces created by the cannonballs they fire, air or no air. In fact, rockets work better above the atmosphere where there is no air resistance. Lift. Using Newton's third law, we can understand how a helicopter gets its lifting force. The whirling blades are shaped to force air particles downward, which is your action, and the air forces the blades upward, which is the reaction. This upward reaction force is called lift. When lift equals the weight of the craft, the helicopter hovers in midair. When lift is greater, the helicopter climbs upward. Birds and airplanes also fly because of action-reaction forces. When a bird is soaring, the shape of its wings deflects air downward. The air in turn pushes the bird up. The slightly tilted wings of an airplane also deflect oncoming air downward and produce lift. Airplanes must continuously push air downward to maintain lift and remain airborne. This continuous supply of air is produced by the forward motion of the aircraft, which results from the jets or propellers that push the air backward. When the engines push air back, the air in turn pushes the engines and plane forward. We'll learn later how the curved surface of an airplane wing enhances the lifting force. So why do objects that experience the same amount of force accelerate at different rates? Our next learning objective is explain why an action force is not canceled by the reaction force. An interesting question often arises since action and reaction forces are equal and opposite. Why don't they cancel to zero? To answer this question, we must consider the system involved. Consider, for example, a system consisting of a single orange. There's a dashed line surrounding the orange and it encloses and defines the system. A vector pokes outside the dashed line represents an external force on the system. The system is the orange. Accelerates in accordance with Newton's second law. So if there's a force provided by an apple, which doesn't change our analysis, the apple is outside of the system. The fact that the orange simultaneously exerts a force on the apple, which is external to the system, may affect the apple, but not the orange. You can't cancel a force on the orange without a force on the apple, so in this case the action and reaction forces don't cancel. Action and reaction forces do not cancel each other when either of the forces is external to the system being considered. So we'll consider a larger system. We enclose both an orange and an apple, and we see there's a boundary by a dashed line. The pear is internal to the orange apple system, so the forces do not cancel each other. They play no role in accelerating the system. A force external to the system is needed for acceleration. That's where friction with the floor comes in. When the apple pushes against the floor pushes against the apple, pushes on the apple, an external force on the system. The system accelerates to the right. So there will be one demonstration that I'll do in class, and there will be a girl and there will be a goat inside of a little cart. And these are both toys. The girl is outside of the system, but the goat exerts a force on the girl. It can affect it, but not the goat itself. The larger system encloses both the goat and the girl. These forces do not cancel each other because they play no role in accelerating the system. The friction of the floor comes into play. The girl pushes against the floor, and the floor pushes back on the girl. The system accelerates to the right. If the action and reaction forces are internal to the system, then they cancel and the system does not accelerate. There will also be a demonstration too, an interaction between a foot and a ball, and that allows the ball to accelerate. If two people kick on the ball, there's no acceleration. That means they're kicking against each other. The net force on the ball is zero. It is equal, opposite, and simultaneous. There is not an action-reaction pair because it is opposing and the forces are acting on the same object. So inside a baseball are trillions and trillions of interatomic forces at play. They hold the ball together but play no role in accelerating the ball. Although every one of the interatomic forces is part of an action-reaction pair within the ball, they combine to zero, no matter how many of them there are. A force external to the ball, such as a swinging bat provides, is needed to accelerate the ball. If the action-reaction forces are internal to the system, then they cancel, and the system does not accelerate. So, my ending question is, why don't action and reaction forces cancel each other? Thank you.